The other type of energy that we will learn is potential energy U. And there are two types of potential energy. First one is gravitational potential energy, or we can write it as UG. And the second one is elastic potential energy, which can be written as US. Okay, the first one, gravitational potential energy. What is it? It is the energy that is stored in a body or a system because of its position. And we can write it in the form of a formula. UG is equal to mgh, where m is the mass of a body, g is the acceleration due to gravity, and h is the height of a body from its initial position. Now there is also work gravitational potential energy theorem, where work is equal to negative delta U. But for calculation, we can use W is equal to delta U, in which delta U is UF minus UI. Let's look at example 5.6. This is a smooth pulley system where a force F is required to bring an object of mass 5 kg to a height of 20 meter at a constant speed of 3 meter per second. So we have the mass, height, and also the speed. Now the information that we can get from here is that constant speed would mean that the acceleration of the system is equal to 0. So initially the object is on the ground, and then it is brought up to a height of 20 meter by the force F. So we can draw the diagram like this, and then we can also draw the displacement of the object. So the displacement is equal to the given height, which is 20 meter. And we know that the object is moving with constant speed, so we can apply the first Newton's law, in which the net force is equal to 0. And then we have to find what is F net. So in this case, we only have motion in the y component, so we only have to look at forces in y component, in which we have force F, and we also have another force, which is the weight of the object. So our net force will be equal to F minus weight equal to 0, and weight is mg, so F minus mg is equal to 0, and then we get F is equal to mg. Mass is 5 kg, and then times by 9.81, and then we get the force is equal to 49.1 Newton. Okay, and then for B, we want to find the work done by the force F. So we use the formula Fs cos theta, and then we have to find theta, which is the angle between force and displacement. So as we can see from the diagram, the angle between them is 0 degree because they are parallel to each other. So now we can substitute in all the values. 49.1 times by the displacement, which is 20 meter, cos 0 degree, and we will get the work done is equal to 982 joule. An alternative would be using the work potential energy theorem, in which UF is minus UI, and then mgh final height minus mghi, which is initial height. Then in this case, our initial height is 0, so we just have to substitute for mghf, and then we get the final answer. The next type of potential energy that we will learn is elastic potential energy US. It is the energy stored in elastic materials as the result of their stretching or compressing. But before we can get the equation for elastic potential energy, we should look at Hooke's law first. So Hooke's law states that the restoring force F of a spring is directly proportional to the amount of stretch or compression, extension or elongation, X, if the limit of proportionality is not exceeded. We can basically rewrite this in the form of Fs, which is restoring force, is directly proportional to negative X. So X is the extension or elongation. And this can be expanded into the formula Fs is equal to negative Kx, in which K is the spring constant. The negative sign here only indicate that the direction of Fs is always opposite to the direction of X. Imagine you have a spring which is in equilibrium position, and then you stretch the spring until it has an extension of X, and this spring will have a restoring force which is in the opposite direction of X. So from here you can get the formula for US, in which US is equal to half kx square, where k is the spring constant and x is the extension or elongation, and then this formula can also be rewritten into half fx because f is equal to kx. Okay, now we can look at example 5.7. We have a force of magnitude 800 Newton causing an extension of 20 centimeter. And then we have to find the elastic potential energy of the spring when A, extension of spring is 30 centimeter, and B, the mass of 60 kg is suspended vertically from the spring. So to solve A, we have to look at the information that is given to us. We have a force of magnitude 800 Newton, and this is actually equal to our restoring force, and this force will cause an extension of 20 centimeter. So first of all, we should convert the centimeter into meter, so we get 0.2 meter. So what's the use of this information? From here, we can find the spring constant using Fs is equal to Kx. So when we are using this equation, we can ignore the negative sign, and then from this equation, we will get K. So K can be used to find the elastic potential energy when extension is 30 centimeter. So now just substitute in the values of Fs and also x, which is 0.2 meter, and we will get our spring constant to be 4 times 10 to the power of 3 Newton per meter. So we want to find the US when the extension is equal to 0.3 meter. To find US, we use the formula half kx square, where k is 4 times 10 to the power of 3 times by the extension square, and we will get 180 joule. And for B, we want to find the elastic potential energy when the mass is equal to 60 kg. So what we have to do is use the same formula. US is equal to half kx square, but right now, when we have mass of 60 kg, we have to find what is x first, or the extension. So when the mass is suspended vertically from the spring is in equilibrium, hence we can apply the first Newton law, in which the net force is equal to 0. To find F net, we have to look at the forces that are acting on the object. So we have Fs and W. Our F net will be Fs minus W is equal to 0, in which we get Fs is equal to mg and Fs is kx. So we get this, and then substitute in the values. So 4 times 10 to the power of 3 times by x, and then m is 60 kg times by 9.81, and x will be 0.147 meter. And now we can substitute x into the equation of elastic potential energy. So US is equal to half kx square, substitute in the values, and finally we will get our US to be 43.2 joule. Okay, now we will learn about principle of conservation of energy, in which it states that in an isolated or closed system, the total energy of the system is constant. This principle is basically telling us that the initial of total energy is equal to the final of total energy, in which we can also write it as the sum of EI is equal to the sum of EF. EI is initial total energy, EF is final total energy. Moving on to conservation of mechanical energy. So we are applying what we have learned from above, but now we are talking about mechanical energy specifically, in which we have kinetic energy and also elastic potential energy. So we can write this as E is equal to K plus U, in which this is constant. So when this equation is constant, we get Ki plus Ui is equal to Kf plus Uf. Okay, let's do example 5.10. We have two objects with masses MP is 2 kg and MQ is 4 kg. They are connected by a light string and suspended, and the object Q is released from rest, which means that object Q has an initial speed which is 0, and if we find the kinetic energy of object Q, we get 0 as well. question is asking us to find the speed of Q just before it strikes the floor. So we want to find VQ. To solve this question, we have to apply the principle of conservation of energy, in which the sum of EI is equal to the sum of EF. And then we have to look at the initial and final situation and identify the energies that are present. So this can be written into Ki plus Ui is equal to Kf plus Uf, conservation of mechanical energy. Okay, let's look at the initial situation first. So this is our initial situation, and then we already established that Kq is equal to 0. And we also have to look at P. So does P have a kinetic energy? Well, we know that the system is at rest, and these two objects are connected by a pulley. So if Q is at rest, P is also at rest. Hence, kinetic energy of P will also be equal to 0. Next, does object Q has potential energy? So it has a height 2 meter. So we know that U is equal to mgh. So that means that object Q has UQ. Okay, what about UP? So we look at object P, it is on the ground. So height is equal to 0. Hence, it doesn't have UP. Then we can look at the final situation. So these two blocks are connected by a pulley. And we know that if block Q starts moving, block P will also move with the same speed. So these two blocks or objects have the same speed V. And we know that if an object has mass and speed, it will have a kinetic energy. So both block or object will have Kp and Kq. And then what about UP? So block P has a height, so it has UP. And for block Q, it is on the ground, so it doesn't have a gravitational potential energy. So its UQ is 0. So initially, we only have UQ. And final situation, we have Kp, UP, and Kq. So total initial energy is UQ, and total final energy is UP plus Kp plus Kq. And then we can expand this into their formulas, where UQ is equal to mqgh, and then UP is mpgh, Kp is half mv squared, mpv squared, and Kq is half mqv squared. And then you can substitute in all the values that are already given in the question to find V. And V will be 3.62 meter per second. Finally, for 5.3, we are going to learn about power. There are two types of power. First one is average power. So PAV, or average power, is defined as the rate at which work is done. So rate and work, which means that it is delta W over delta T. We can also define power as a rate at which energy is transferred. So we can write that as delta E over delta T. Okay, and then we have instantaneous power. So instantaneous power is power at that instant of time. And we can define it as P is equal to Fv cos theta, or we can also write it as a dot product between F and V. And F is the magnitude of force, V is the magnitude of velocity, and theta is the angle between F and V. For the SI unit of power, we have three. The first one is kg meter square per cubic second, and then we have joule per second, and finally we have watt. Then we also have another unit, which is horsepower. So 1 horsepower is equal to 746 watt.